Here we have the longitudinal dynamics of the aircraft, in which comprise of the Phugoid mode and short period mode, and here are the linearized state space equations for the system, which we can then write in matrix form, and then we can manipulate the matrix form to give us this form here. Now in this form we can extract the SPO mode and the Phugoid mode approximations, and that's what we're going to do next.
Good morning. This morning we're going to look at approximations to the SPO and Phugoid modes, which result from looking at the 4x4 matrix for the longitudinal dynamics. In the longitudinal dynamics we have four variables: u, forward speed; w, vertical speed; q, the pitch rate; and theta, the pitch angle. Now in this matrix it's a 4x4 matrix, and it contains two second order modes. So one of the second order modes is the SPO mode, and the other second order mode is the Phugoid mode. Now to extract these from a 4x4 matrix, we could do it by working out the eigenvalues. But if we work out the eigenvalues of a 4x4 matrix, it's quite hard. So we can come up with approximations of the SPO and the Phugoid by reducing the 4x4 down to a 2x2. And there's two different techniques for extracting the SPO and the Phugoid. So let's start off with just a quick recap of this matrix. Not all the numbers in the matrix are important. This is XU over M, ZU over M, and U0. And those three are important for getting the Phugoid mode. And if we call this one A, B, C, and D, that's the middle four, those are useful for extracting the SPO mode. So let's start off by looking at the SPO mode. Now, we can do that by extracting the middle four here to obtain our SPO mode. So we could take out the A, B, C, D and reduce it down to a little 2x2. Then what we've got to do is compute now the eigenvalues of this. So this is computed as determinant of Si minus A equals 0. So we could compute this now for this particular matrix. So it'd be S minus A minus B minus C S minus D equals 0. So that's the S there from this, Si, then minus A, so it's minus A, minus B, minus C, minus D. Now for a 2x2 matrix, is this times this minus this times this. So it's going to be A, S minus A times S minus D minus BC equals 0. So we've got that times that minus that times that. So we've got minus times minus times minus gives you a minus. So we can expand this out now as S squared minus A plus DS plus AD minus BC equals 0. Now this does give us a second order system equation. Now the important thing about second order systems is we can represent them by this type of expression: S squared plus 2 zeta omega n S plus omega n squared. So this expression here now is the same as this one. So we could rewrite this as S squared plus 2 zeta omega n S plus omega n squared equals 0. So the important thing here now is that this term here is the same as that one, and this term here is the same as this one. So we could now use that technique to work out omega n and damping ratio. And we can do that by, as a worked example, by taking some numbers here from this numerical case here. So in this particular case now, this is A, this is B, this is C, and this is D. So we could put the A, B, C, D now into this expression here, and then compare it with this one. So I'll just briefly rub this out. And put in the numbers. So it's going to be s squared plus, and it's going to be, because the minus sign here, the minus takes care of these minuses, so it's going to be 0.3149 plus 0.428 times s plus, that's AD, so that's going to be that times that minus that times that. So the minus times minus the plus, so it's going to be 0.315 times 0.428 plus, so it's going to be that minus that times that, so that minus sign becomes a plus again, so it's going to be plus 0.0034 times 235.9. So we can now work these out, and we get this term here comes out as 0.734, and this term here, if we work on out, that comes out as 0.9369. So this term here now is the same as omega n squared. So if that is omega n squared, if we then take the square root of this, we'll get that omega n equals 0.9679 radians per second. And then we also have this term here is 2 zeta omega n. So we've got 2 zeta omega n is equal to 0.734, from which we can now get zeta. So zeta is equal to 0.734 over 2 to omega n, which is 0.9679. So if we compute that one, we get a zeta of 0.3838. So what we've been able to do now is start off with the middle 4 elements here, the 2 by 2 matrix, compute a determinant of a 2 by 2 matrix, expand that out into second order system form, then do a compare coefficients to obtain omega n and then damping ratio. So that's how we could extract the SPO, approximate SPO mode from the big 4 by 4 matrix. Now the next one to do, just make a bit of space here. Next one to look at is the Phugoid mode. Now the Phugoid mode is easier than the SPO mode because we can recall that the equation for the Phugoid second order mode is given exactly by this equation here, x, or it's an approximation, but it's the equation we're going to use, s squared minus xu over ms minus gzu over mu naught. So these parameters now, that's xu over m, zu over m and u naught, you can obtain directly from the diagram here. So you can see xu over m sits there, so that term sits there, zu over m sits there, and u naught sits there. So it's possible now, because again this equation here now is exactly the same as this one here. So we can do s squared plus 2 zeta omega n plus omega n squared equals naught. So this term here is omega n squared, this term here is minus 2 zeta omega n. So next thing we can do now, we can go for the omega n term. So you know that omega n squared is minus g zu over m u0. Now zu over m is this term here, which is going to be minus 0.0905. So the minus times the minus gives us a plus. So it's going to give us 0.0905 905. That's that ZU of M. We've got G, so G is 9.81. And then we divide by U0. And the U0 sits in there, which is the 235.9. So now we've got an expression for omega n squared. And that comes out as omega n squared comes out as 0.004. Now if we take the square root of that, we get that omega n comes out as 0.0631 radians per second. So that's how we've quite simply got to the natural frequency of the phugoid. We also know now that 2 zeta omega n is equal to xu over m, and xu over m sits up here. And it's also got a negative sign in front of it. So the minus times minus a plus, so we know now that xu over m will be 0.0069. That's the xu over m. And xu over m now is equal to 2 zeta omega n. It's going to be 2 times zeta, and the omega n is given by this term here, so it's going to be given by 0.0631. So there's our xu over m with the minus sign taken out. There's the 2, there's the zeta, there's the omega n. So we can get this now. Zeta is equal to 0.0069 over 2 times 0.0631, and that comes out as 0.0562. So this is the alternative to the phugoid mode now. We do a slightly different approach to the SPO. We go as a direct parameter drop down from the matrix. We start off with ZU over M and U0 to get the natural frequency, and then we use XU over M to get us to the damping ratio. So for this particular example, the natural frequency of the phugoid is that one there, and this is the damping ratio of the phugoid mode. So that's how you can extract SPO modes and phugoid modes from the original 4x4 matrix. And we only need to know 6 numbers to extract them.